Welcome to section 2.3, differential equations. This section is mainly about applications, and so the algebra involved can be horrendous. So use all tools available to you to make your life easier. In real life, when you want to solve these problems, you're going to be using tools. So grinding it out by hand, while nice, you want to be able to get the correct answer. So if using tools helps you, do so. All right, so in problem 1, we have a sports car. Its acceleration is proportional to the difference between 250 kilometers per hour and the current velocity of the sport car. If the sport car can accelerate from rest, velocity 0, to 100 kilometers per hour in 8 seconds, how long will it take the car to accelerate from rest to 200 kilometers per hour? So in the very first part of this, I just copied from the solution manual what they did, but their numbers are a little bit different. I put it here because it's nice and neat and it's easy to read another example. So looking at our particular numbers. All right, so proportionality constant. V at 0 is 0. V at 8 is 100. All right, so I'm going to separate this problem. So all the v's are on one side, just the constant k on the right. Multiply through by a negative, so I'm integrating the left, which we know is a integration by substitution, but it is going to be a natural log of that item minus kt plus c. I can take e of both sides, and so I get the inside part. E to the minus kt, e to the c, we just call c. All right, and so if I move the 250 over, we get a relationship here for v of t. All right, so at times 0, all right, times 0, I have 0 equals 250 plus c. So c is a minus 250. All right, so here's our basic relationship for the velocity. What I'm missing is k, the rate. So to find k, I need to plug in what I know, and that is at 8, we get 100. All right, so plug in 8 for time. And now start cleaning this thing up. Move the 250 over. Divide by a negative 250. All right, so it's getting better. I can use natural logs to solve it. And so I get an approximate number for k. And so here's my velocity. And so what you can see here is as time goes to infinity, it's going to reach a limiting velocity of 200. 250 never gets there, but asymptotically. And so the question is, they asked, how long to get to 200? And so I made a graph of v of t. And so graphically, you can see this is, let's see, 10, 20, 40, 60, 80, so 20 something. It turns out to be around 25.2. So set our expression equal to 200, grind away until we finally can solve for t. And so you get about 25.2 seconds to reach 200. All right, in question 2. Suppose that a car starts from rest. So again, the velocity is 0 when we start. We have an acceleration of 5 feet per second. We have air resistance that's decelerating. So find the car's maximum limiting velocity. how long will it take to reach 80% of this limiting velocity? And how far will it go when we do that? So again, I copied from the solution manual what they did for slightly different numbers. In their case, they went 90% of the limiting velocity. But it's nice and neat, probably looks better than all my writing. But for our case, plugging in the numbers, we have 5 minus 0.05 v. So factor out the 0.05. Separate variables, integrate both sides, and then get v of t by itself. Use our initial condition that v at 0 is 0. And so if we do that at 0, we get that c is minus 100. All right, so looking at that, what I see is as t goes to infinity, this term is decreasing to 0, and so the maximum limiting velocity would be 100. All right, so looking at that, I graphed our v of t. So here's my v of t. Here's my limiting of 100. We want to get to 80, which is 80% of the max. And so we set 80 equal to our expression for v. Start solving. And finally get that this is about 32.1888 seconds, which you can see here from the graph of v of t. This is in 10, 20, 30, 40. Here's 50, so a little bit bigger than 30 on the graph to reach that point. And algebraically, we got the exact number of 32.1888. All right, so if I want to find out the distance, I need to integrate velocity. So if I integrate the 100, I'm going to get 100t. If I integrate this term, I can take the 100 out. I'm going to do the e by substitution, so I'm going to get a 1 over 0.05 with a minus. But that minus will make that minus go away to a plus, and 100 divided by 0.05 is the 2000. All right, so we know at time 0 we hadn't gone anywhere, so c then is minus 2000. All right, so I have a relationship here for the distance. We know how long we want it to go, which we found previously. So plug all that in, a bit of grinding away, and we get 1,618.88 feet. So yes, a lot of calculations and again, a lot of algebra. All right, question 3 probably has the most algebra. So let's see what's going on. A woman's in an airplane and the airplane is at 15,000 feet. She jumps out of the airplane and she falls freely for 19 seconds. Then she decides to open up the parachute and go to the ground. Now we have air resistance here, and the air resistance without the parachute is 0.13. With the parachute is 1.3. So, what is it we want to find? How long will it take her to reach the ground? So, we already know there's 19 seconds here. The question is, what's the time on this part? But we have to figure out what's going on here first. So, my formula is g minus rho v. So let me put some minuses here because g we're just using as 32. All right, so minus 32 minus 0.13 v, my initial rho, for air resistance, and my initial velocity is 0. Okay, that's when we first bail out. And then when I solve this problem again, I've got a different proportionality for air resistance. My velocity at that time is going to be whatever the solution here is after the 19 seconds. All right, so we start integrating on this side by substitution. All right, so both sides. At that point, I want to clear away this term, so I'm multiplying by negative rho over 1. All right, so I can distribute this in, but I'm going to call this thing a new constant c anyway, e of both sides. All right, so now we grind away, keep going, and we get an expression for v of t. So my v of t depends upon rho, gravitational constant. All right, so at time 0, velocity was 0, and so c then is g over rho. So here's my expression for v of t. And so now if I plug in, g is 32, rho was 0.13, put in my decay, and I'm doing this from 0 to 19. So I plotted that using Desmos online graphing calculator. All right, so here's my expression, and I also made a table 0, 5, 10, 15, up to 19, and that's the number I need. I need the velocity when we are at 19 seconds. So minus 225.33296. All right, x of t at that point, I can integrate the velocity. All right, so we're doing all that. So at time 0 here and there, we know we were at 15,000 feet, and so I get that c is 16,893.49112. So there's my expression for x of t. And so again, I plotted that. Why do I plot that? Well, because I'm going to need to know what is the height I'm at after 19 seconds. All right, so again, I plotted that so you can see the numbers are going down. And I made it in a table format again because I wanted to know what's going on at 19. So we started off at 15,000 feet. We fell 19 seconds. After 19 seconds, here's my new position. Here's my new velocity. Velocity is negative because we're going down. So I need to solve the equation again with a different proportionality constant because the parachute has now opened. I have a new initial velocity. What we did previously is still valid, and so I can plug most of that stuff back in with my new V0. And so I get a relationship for the velocity going forward from 19. All right, but I need to know x of t. All right, so x of t is the integral of all this junk. So somewhat messy. And I need to plug in at time 0. We left off at 12,056.40 feet. And so I get a relationship for x of t. This would be a mess to solve by hand. So you're going to have to use an online tool to figure this out. I did. I used Wolfram Alpha, which solved this for me and got 483.518 seconds. That's on that part. So it took 483 seconds to fall from 12,000 to the ground. That's where the zero, why it's zero. Add that to my initial 19 seconds, so around 503 seconds. So this is a difficult problem. Lots of algebra, easy to make a mistake. So there is some shortcuts that you can take. Again, you can use some tools. So you can use Wolfram Alpha to solve the basic differential equation with its initial condition. And so I quickly get what's the velocity. You could do, again, you type this stuff in and integrate it to get x of t. That will work. And then I used it again. You can use it again to solve the new problem with your new velocity, and then it will give you v of t. So use your tools as needed. Don't struggle with terrible, ugly algebra. It really is very easy to make a mistake, and no need getting completely confused and frustrated. The last problem is fairly straightforward. You're standing on an asteroid, has a certain diameter, and they tell you some more information about that. And the question is, do you have enough escape velocity to jump up? And so I put it in here, what they did from the textbook. It's fairly easy to read what's going on. And you can see that, yes, you would be able to have an escape velocity off the asteroid.